Okay, so the next speaker is Fitz, who's going to talk about how tidal disruption events shine in optical and in radio.
Hi, I'm Fitz. I'm a PhD student at Monash working with Daniel. I'm just talking about TDEs today. So first of all, what is TDE? So it happens when a star approaches supermassive black holes and due to the strong tidal force of the black hole, or like if you want to think in the GR way, it's diverging geodesics, which cause the star to disrupt it into a stream instead of like a self-bonded star anymore. And this one key radius, which is called the tidal radius. So at this radius, the star's self-gravity will equal to the black hole's gravity on the stellar surface. So basically past this radius, you're no longer like self-bonded star anymore. And this debris stream will like come disrupted, go out and come back, and fall back to form some kind of accretion disk and launch outflows. So on observational side, we got a lot of observations. So we saw them in radios, in infrared, in optical, in X-rays, and also like PeV neutrinos. And with PeV neutrinos, it's also like predict to have gamma rays, but it's not been detected yet. So with all those like different kind of observations in different bands, it's like we don't have one unified theory to explain all the radiations. So, and in this talk, I focus on radio and optical, which is the thing I've been working on. So people have proposed a lot of models trying to explain where does the optical emission comes from. So basically just by like imagine colliding different things like disk stream and stream with stream, disk with disk, just imagine all kinds of collisions to form optical radiation. But we still don't know which one is really the case or which one is like more dominant. So that's why we want to use phantom to like do an actual global simulation to see what's the case. So to do that, we are using GSPH of phantom, and we start with one solar mass real solar star, which is evolved from MESA and then mapped into phantom. So the mass of the black hole is like 10 to the 6 solar mass. And for the sake of time, we choose some like rather unphysical parameters, which has like eccentricity of 0.95 and really deep encounter. So the tidal radius is like 5 times the pericenter radius. So in this case, it will be disrupted really fast, so have a shorter time scale, so it's easier to simulate. So here is a video of the simulation. We start with that's the star, and we have the black hole somewhere in the middle, and we have the star come to the black hole and got disrupted into a string. And then the string fall back, and due to the GR effect, there's like GR precession, it forms some kind of like self-collision, so colliding with itself, which causes a rapid dissipation of orbital energy and circularized into some kind of disk, which then dissipates. So that's like really close into the scene. So if we zoom out and look at large pictures, so here on this like this little triangle basically represents the scene you just seen in the last slide. So, and we also lower the rendering density, so we will see that's like a lot more going on. You got lots of outflows going on, and outflow has velocity of around 0.1 speed of light, and also temperature is still high, like 10,000 Kelvin. So now if we add some opacity into it, which is just the electron scattering opacity here, and we see it's like some kind of opaque gas blob. So if you look really far away, it's probably just look like a gigantic star with some alpha, red giant. Yeah, so that's it for optical. Just leave that aside for now. And so in the videos, you see like there's like lots of outflowing going on, and like in the galactic center, so around the supermassive black hole, we expect there to be some like pre-existed gas. So those outflow will collide into this pre-exist interstellar medium and form shocks, which could amplify the magnetic field and accelerate electrons to form synchrotron radiation, which is thought to be what we observe in the radio band. So we also do this kind of simulations, and we just create some like surrounding interstellar medium and with some density, power low density profile. And the outflow is like something we newly implement into Phantom. So we took the previous simulation and took the outflow and inject into this new simulation. So it just like keep creating outflow from the inside. So in this case, instead of assume some like spherically symmetric outflow, we actually using the real outflow in the previous simulation. So here is like the shock layer form, just nothing fancy, just some expanding shock layers. Yeah, and it's very aspheric. It's like an egg. So then we basically use phantom analysis to analyze this shock layer, and we just got the maximum radius and maximum velocity of that shock layer and compare to some observations. So here the solid lines are our prediction from the simulations, and all these like other things are the different kinds of observations. So one problem with radio observations is still like they are really unsure about what they observe. So it's kind of hard to like compare. Yeah. So then we use Splash to do ray tracing. So instead of MC-Force, which actually we cannot use MC-Force. MC-Force doesn't have electron scattering as not like synchrotron radiation. So we just use Splash to do some really easy ray tracing. So we start with some incoming radiation, and when it reaches a particle, we add a like contribution from the particle and going on, just stacking on top of each other until it reaches the observer. So although we use like radiated transfer equation to do all these kind of things, it's still rather simple like estimations. So then we come up with like some synchrotron and also lightcurves. So this is for optical. And here again, like all these lines are our predictions and the dots are from the observations. So although like our lightcurve is not really follow the trend of the observations, it's about the same order of magnitude. And given we didn't like fine tune the parameter in any ways, it's quite a good like agreement with the observation. So it kind of proved like thing we do like all the observation is truly a TDE. Yeah, so that's some images for the front, like in the radio band. So instead of those like the shock layer we just see, it's like really, I don't know how to describe it, but looks fancy. So we also have some spectra. As I said, the radio people doesn't really know what they're observing. So when they try to infer those like radius and velocity thing, it's not that trustworthy. So instead we just compare our like synthetic spectra with the observed spectra. So we see in the like observed ones, the peak frequency kind of shifting from right to left over time. So we also got same behavior that shifting from right to the left. So one thing it doesn't really match is like the peak flux. So the flux kind of change over time. So what rather like decrease over time or like increase then decrease over time. So what we have is basically constant over time. So this could be due to like our lack of cooling, which is a really hard thing to do. I kind of have no idea how those cools. Yeah, so that would be like in the future works. And yeah, I just want to basically touch on this thing. So this is very preliminary work. So there is a long-lasting problem in the TDE simulation field. So due to like the orbits being more condensed around the pericenter, the stream would actually be compressed when like passing through the pericenter. So in that case, we form some shocks they call nodal shock. But so through this nodal shock, like it dissipates some orbital energy into heat, but the amount of heating is really resolution dependent. So here's the 5-year-old paper from Daniel, like show some resolution study of the nodal shock. So as we increase with resolution, the shock heating is like decreased by large amount. So, but it's clearly not converged yet. So then we try to use APR for this one. And actually just skip that. So actually we got some pretty good results. So the original simulation we got is only like 100K particle, 1 million, 10 million particles. So we then add APR region around the center of the black hole and just keep increasing the number of particles. So we kind of get a converged resolution when we have like 12 level splitting. So if you count the number of particles, 12 level splitting is like equivalent to around 40 billion particles. So if we really want to do like a global simulation with a converged result, that's basically impossible. And yeah, that's all for the nodal shock part. I haven't like do any analysis on that yet. So that's the conclusion. And the models basically we use the like the colliding for the optical radiation and also the colliding with interstellar medium for radio emission is kind of correct because they all kind of agree with the observations in ballpark. So basically that just prove people's theory, kind of. Yep, that's it.
Thank you very much for the talk. So are there any questions from the audience?
In the example of the nodal shock that you showed just now, when you use IPR, were you using also the merging when it goes out, or do you have like only IPR for the splitting and just like keep the stream?
No, so like the layout splitting is kind of like that. So it's centered around the black hole and just like increase. So it does merge as it goes out, but actually we don't care that much because the only thing we really interested is like around the nodal shock, like amount of heating from the nodal shock. So as long as it passed the nodal shock, we don't really care about it.
And in terms of total number of particles, instead of 10 million particles, how much is it with like the 20 APR levels in total?
I think at this point with 20 level, it's around, so like when before we do the APR, like I kind of chop out like other thing outside some radius. So it starts with only like around 60,000 particles. But like basically when you're at this point, it's coming back to around like 40 million particles. So it increased by like a crazy amount.
I wanted to ask about this as well. I know that you've edited the API ever so slightly in a way that makes this problem very, very good. Can you talk more about that, please?
Yeah, so because like this is in like info.gr, so when we usually do the splitting, like basically like tangential to the splitting radius, it kind of just split particle into different energy orbits, which is really critical like at this moment. So the thing I was doing now is basically when the particle needs to split, I kind of track it back and forth through its like aligned geodesic and to find the like correct position and velocity. So, and I did check like the energy of the particle compared to just like splitting along the velocity vector, and the energy is like if I split along the geodesic, the energy is like almost equal between two particles, so that's good. And if you just do like splitting on the velocity vector, it's not that equal.
Sure, you have a question?
Basically, does it mean your API should be coupled to the geometric of your space-time? Is that true? They're already coupled. Is that
Yeah,
what
it's already coupled.
I see. Cool. One more question. So from your outflows, do you see any reverse drops that feeds back to the black hole?
I think there might be, but outflow velocity is just too huge. You can't actually distinguish the reverse
So
drop.
the outflow velocity is going out. But usually, if you happen wherever black hole goes, you would see a reverse shock that goes back inwards.
Yeah.
Become an implosion kind of thing. So does it go back to the black hole, and does it affect your kind of disk around it?
I never formally checked, but I did have a brief look. So the shock velocity, just because the shock velocity is kind of like the speed of sound, and compared to the outflow velocity, it's still like the outflow velocity is higher than that velocity, so it never goes backwards. So even the reverse shock is still like outflowing.
Do you consider the effects of acceleration by radiation on the outflows?
So for this one, no, but it's also kind of like accounted because like in central region is basically very optically thick, and we are just using adiabatic. So basically that's like same as all the radiation is trapped and just increase the pressure to produce this outflow. So it's not really like the radiation is powering the outflow, but kind of like that.
Questions? Okay, if not, let's try this again.